Well, I think we can start, folks. Looks like it's official. Welcome back, everyone. Looks like we're pretty much a in-person only class today, so that's kind of cool. We can probably minimize that one there. But any questions at all, folks, before we get started today? Okay, well, just for the quick rundown of announcements, it wouldn't feel right if we didn't do them. We have quiz number 5 is going to be due tomorrow, so those will always be due on Thursday. And I'll have the 6th quiz posted. Quiz number 6 is going to be pretty pivotal, I'd say, because it's going to be based off chapter 6. And chapter 6, this looks like it's going to be the last chapter that's going to make it onto exam 2. I don't think I have enough time to rush through chapter 7 to get it done this week. So we'll probably be mostly done with chapter 7, but we'll finish it on Monday of next week. That means this will be the last one on the exam. Quiz 6 will be definitely a chapter 6 problem. And chapter 6 is kind of touchy. It requires this setup right here. I'm not going to ask you to produce a scatter plot on your calculator, so there's less worries about that. That's more to help out with the homework. But on the real exam 2 and on the quiz, you may have to calculate a correlation coefficient. And so this will be the thing that you have to be prepared for before the exam. So in other words, if you feel pretty good with computing all the things in your calculator on quiz 6, then you're going to be all set up for the second exam. Second exam is going to use this function quite a lot. Second vars, so you'll be using normal CDF inverse norm, and the other things that we'll be doing here in chapter 6 as well. So that's our goal so far today, folks. Finish off chapter 6, get started on chapter 7, but majorly with an eye towards how to get those calculator things to come out just right in time for the exam. Any questions at all with what we've got with announcements? Okay, so that's where we're going. And in the future here, towards this weekend, again, we'll start seeing more information filled out right around here on what the exact coverage is and the sample problems. But here's where we're at so far, right here on example 5. We looked at data like these before. This one has to do with median worker pay, so 50th percentile. But this time we're taking a second variable into account. We're comparing the median worker pay for these different companies against their percent change in stock price. So that'll be kind of interesting in a way. The write-up of the problem goes off to say, the article, 115K, the best 13 paying US companies. This was USA Today, 2015, so it's already like almost 10 years out of date. But anyways, it gave the following data on median worker pay in thousands of dollars and the 1 year percent change in stock price for the 13 highest paying companies in the United States. And so maybe the thought is the more the average worker, the median worker rather, is getting paid at the job, maybe that's going to translate into higher job satisfaction, better performance, and the whole company may do better. Who knows? But that's what the question that they're trying to answer here. So if we look at the data, say, for example, Netflix, this is old data. Netflix is not doing as good any longer, but back in 2015, they were doing fantastic. Median worker pay was nice, $132,000. That was a lot in 2015. And their stock price jumped up by nearly 100%. So that was an incredible performance for them. Does the trend continue? Well, here's Yahoo, but they've always been kind of a struggling company since the 90s. So, they pay everyone a lot, but we're not expecting a lot of growth at Yahoo. The fact that they didn't lose value is probably the good thing for them. But then there's other companies that might feel more like an outlier, say eBay. People are paid pretty well, yet that one lost value, almost 50% of its value year on year. So that's the context of the data. What we want to do is not just highlight cells to try to paint a picture of these data, but really look at appropriate graphics. We need a good scatter plot going on. We want to measure the association, decide if it's linear, its direction, and all that fun stuff. Any questions about the write-up with the context? Okay, so let's get started. It says, use your calculator to construct a scatter plot of these data. Again, on a real exam, I'm just going to show you the scatter plot, so there's not as much worry there, but let's still do this anyways, just for the sake of helping out with the homework. So I'm on the wrong menu here. You can hit second, and then the quit button under mode to get out of there if you're just not in the right menu. Next thing you have to do is import these data. This right here is going to be our explanatory variable. we're hoping that the median worker pay explains how the percent change in stock price behaves. So this will be the response variable. And just like I mentioned before, usually data sets are formatted in just this appropriate way. The explanatory variable usually comes first column or the first row if it's stacked sideways, and the response variable should come second. This right here is not the variable, that's just the identifier in the problem going that way. So here, the response, keep in mind that always goes in L2, explanatory always goes in L1. So with that out of the way, first thing we hit is the stat key, hit enter right away. And you probably have data in your calculator. So trick is use the left key, up arrow key, so that L1's highlighted. Hit clear and enter, wipes out L1. Right arrow, up arrow, and do the same. Clear and enter. Now you should have a clean slate. If L1 ever goes missing, then that's something you can bring back as well. So let's start putting these in really carefully. I'll get quiet while everyone works on the data import. Once you get to the bottom of a row, it's good to double check what this says. It says L113. The data had 13 values. That means I messed up. I need to find where I missed a value. I thought I got that in there. I'm not too sure where I messed up. Oh, that's probably what it was. I'm just going to override these and start putting in the correct values. I think that's the easier fix on here. You can't necessarily put it on the end unless you're very careful to put 5.2 on the end, but I would just lose track of that. So I'm just going to start over and overwrite my data starting at 121. Thanks for spotting that. 121.2. The way you want to do this is not do what I'm doing. You want to go slow and methodical, or else it's super easy to make a mistake like I did. It looks like I have column 1 in, and I'll start over on column 2 and actually go carefully. And this last one is touchy. Whenever you see a negative sign like that, it's tempting to press the minus sign, but that'll give you a syntax error. Recall you've got to use this one, very bottom, negative 44.7. Okay, I think I've got all the data in finally. Anyone needed any additional time? Okay, no worries. Looks like we're just about there. Anyone need any additional time? Okay, kind of boring, but this is the experience in stats. It's sometimes really mind-numbing methodical data entry. So we get that experience in class every now and then. After putting in all the data carefully, hit the stat button once more. On this menu, you want to go over to calc for calculate. And the option for the scatter plot is way down. Oh, hang on. I'm mixing up with what I want to do before. This is getting the actual correlation coefficient. So that would give us the correlation, but to get the scatter plot, that was the wrong step. Anyone recall what the right step was? Good call. Thanks, folks, for remembering that step. You hit the zoom key for the scatter plot. You go down to option, I think it's 8 or 9. Option 9, good call. Thanks for saving that one though, folks. I felt like I was in the wrong menu all of a sudden. So hit the zoom key, go down to option 9, and this is what you should see in your display after taking those steps. So we've got it, folks. That's our scatter plot. Kind of a weird looking scatter plot, but let's take a look at what we've got. Let me move that red dot out of there. Okay, so just as a really quick reminder on the notes, this is provided on exams. It probably won't be a screenshot like this. It'll probably be a different program, but you'll see essentially a scatter plot to work with and visualize. Looking at this, well, we have a horizontal line segment and something that looks like it's on a negative value. We want to investigate that further on the calculator. You can hit the trace button right here. When you do that, you should have a coordinate that's flashing. Mine's on the very far right. And left arrow will take you to different values. Usually, let's see what else could I press up. The right arrow is taking me to the different values. And looks like if I go all the way to that one, this is the one that lost 44.7% of its stock price. So that value there, that one was eBay. So looks like that's a pretty unusual value, but maybe so are these as well. They're pretty far out there. One, let's see, what could that one have been? Left arrow can take us back to this one. This was at 134,000 pay, 134.7. That was Jupiter. So interesting data values. But let's see, what were we asked to do on this one? Use your calculator to construct a scatter plot, treating median worker pay as explanatory variable, percentage stock change as a response variable. So, oh, didn't mean to delete it, but it looks like we did the instructions to the letter. So now we're ready for part B. It says, calculate the correlation coefficient R rounding to 2 decimal places. Then right after, we'll give a practical interpretation using the context. But before we even do that, we want to decide, is a straight line even a good model for this thing? Let's visualize putting a line to these data. It would look maybe about like this. And, well, maybe if we move it up or down or around, might not be doing too bad of a job. I would almost wonder if it could be a curved relationship would do better. But if we're thinking of using the correlation coefficient R, that's the problem's way of indicating that this was linear data for this one example. Kind of strange, but again, it's not a bad idea to wonder, could a different line have done a better job? And maybe, yeah, a curved line looks like it could have modeled the data better. But nonetheless, if it's asking us to calculate the correlation coefficient R, we are treating the data as being truly linear. So that's our line that models the data best. And to do that in the calculator, that's where we go back to the stat key. These were the instructions I was trying to show earlier. But even if you do these instructions perfectly, your calculator may not actually give you the correlation coefficient. So let's go through this one-time setup one more time. We need to go back to this document right here, the TID4 correlation coefficient setup. The nice thing about it is it only has to be done one single time. So the instructions say, first thing we need to do is turn on diagnostic on. How you do that is you hit the second key, then press the catalog button. That's the number 0 at the very, very bottom. If you did this in class with us at the very end of Monday's class, you're probably all set and you don't have to do it again. But if you did it again, there's no harm done. So hit the catalog button there, and we scroll to the diagnostic on option. This is all alphabetical. This is every function in your calculator, so it's kind of an impressive list. Go down till you start seeing the D's. Kind of interestingly, though, Greek letters gets mixed up in this, so they have it alphabetized according to English and Greek all at the same time. Kind of interesting achievement. So down, 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 eventually, that's the one we want right here, diagnostic on. Hit enter on that. Your screen should just say diagnostic on, but it's not done. Hit enter again, and that's what you're looking for. If your calculator says done right at that step, then you never have to do it again unless the battery fails, the memory battery fails, something like that. Your calculator gets reset. You may have to do it again in that context. Any questions, folks, with doing that operation? Okay, once we all have put that in, next thing to do is hit the stat key, go over to calculate, and we're looking for the option that goes like this. Now notice there's some kind of similarity here. This is linreg, stands for linear regression, ax plus b, and then down to option 8, same function, linear regression, a plus bx. Now, what in the world's going on with that? That's pretty strange, but sometimes people write their linear equations this way, ax plus b. That's what you would do in a math setting, y equals mx plus b. But in statistics, it's written this way more often than not, a plus bx. Either option is going to give you the right correlation, so that's kind of nice. But I encourage you to use option 8, because that will make a difference in chapter 7. If you use option 4 in chapter 7, it'll work, but you have to translate to realize that your a value is your slope and your b value is your intercept. It's going to be given to you backwards, or just go this route, and it's a lot more straightforward. I'll always use option 8 just to avoid the confusion on that. So hit enter there. This is what you should see. List 1 for X, list 2 for Y, and everything else should be blank. So if you have anything right here, I just assume you bought a used calculator, someone did something weird there, or maybe you lent it to a kid, brother, or sister, and they were just playing with it. But just delete anything that could be there or there. Hit enter a bunch of times, and finally, you go to this screen. This did a lot. The A coefficient, the B coefficient, this is all chapter 7 stuff. We have R squared, but that's not what we want. That's called something else, the coefficient of determination, if you're curious. What we want is the Pearson's correlation R, the option on the very, very bottom. And by the way, turning diagnostic on, all it did was give you these last two values, R and R squared. So in our problem, R equals, let's see, it says 2 decimal places, so 0.58. Well, we did, folks. That's actually a really, really long computation. It could take probably all of class, all 70 minutes to actually calculate this by hand, and no guarantees we got an accurate value in the first place. It's such a long slog to get through all that. But our calculator doesn't care how much data you give it. It's going to be just as fast as that. Any questions at all? Anyone getting something different for correlation? Okay, now we get to do the fun part of giving a practical interpretation of this value using the context. Let's make this seem more dire. Let's put this in yellow. On a real exam, even if you got this value wrong, I would just assume maybe one of your data values got imported incorrectly. You might lose, say, like 1 point out of 5. Most of the points on this kind of problem is the actual interpretation. So here's one thought you could do. If you like, you could go over here. You could include this on your sheet of notes for exam 2 and observe our value is here. So we'll say that there's a moderately strong correlation between the two variables. We're at about 0.57 right here. It is just a rule of thumb, but it's a good starting point. So coming down below, we can say there is a moderately strong positive. We're saying positive because the direction of the scatter plot is positive as we observe the line, and so is the correlation coefficient. If R was negative, our line would have been going down instead, and we would have said the relation is negative. So there's a moderately strong positive relationship between, we can't say between the variables because we need to pull in the context. That's where we might want to look at the problem again, reread it, something like that. But here, that's the explanatory variable, median worker pay. So that's the x-axis. And the response variable was percent change in stock price. That's the y-axis going this way. So it looks like we're saying as the median worker pay goes up and up and up, there's change in stock price is also going up. There's some outliers to that don't fit the pattern very well, like this one, most notably, I'd say. The rest of the data values seem to actually fit that. The one that was paid the very least, that was eBay, and they're at the lowest end of their stock price change. So we'll say there is a moderately strong positive relationship between the median worker pay and the percent change in stock price. So that would be something that I would be expecting for a question like that on a real exam. You could say a whole lot more, but I feel like this really conveys it. When we said that there's a positive relationship, we already basically said that as the stock price, or excuse me, as the median worker pay goes up, so does the stock price. So you wouldn't have to re-say that if you just said that there's a positive relationship. So really bringing in the context was just saying what the variables were, and you hit that pretty well in this kind of problem. Any questions at all, folks, with the write-up for this one? Okay, so that's analyzing two variables at once. It's kind of nice, except the one thing that we're still not able to really do with any of this is we can't make predictions based on our data. We have an open mic, but no worries. So I think it must have been a cat. I think that was probably the likely explanation. So what, I've lost my train of thought. Oh yeah, so the one thing that we can't do is we can't make a prediction. Notice you might be interested of what if someone was paid this amount? How much would they get paid? Well, you'd have to find the point on that line. We can't do any of that until we actually construct the line. So that's what we're really going to be doing in chapter 7. And this is kind of like a preview to that kind of work, starting to think about two variables, plotting them, and just saying what we see in the plot based off the correlation. So that's where we're going. Looks like we still have one additional question on the notes, but any questions or comments so far? Okay, part C, the last question of chapter 6 says, the article states, they're talking about the USA Today article that this data came from. The article states that the companies that pay more are seeing a payoff in their stock performance. Is this conclusion justified based on these data? This is kind of an open-ended question. So what would you all say to a question like that?
I don't know if there's a chat.
Oh, sorry for the chat or missing it. Oh, no worries. I thought it was something like that. No worries, Courtney. Other questions so far? Okay. Well, one thing you could say to this, the article says that companies that pay more are seeing a payoff in their stock performance. Maybe that's true, except you might say that there's an exception, right? These are the 13 highest paying companies, for example, but one of them, maybe that's the bottom of the list here, saw a huge decrease in the actual stock performance. But that was one value, just an outlier you would say on these data. So there's a lot of different kinds of responses you could give. But here's the response I'd be thinking about. Article states that companies that pay more are seeing a payoff in their stock performance. That's actually a dangerous thing to say. And the reason for this was, since the 13 companies is not a random sample, we have a pretty big problem. It's definitely not a random sample because they said it's the 13 highest paying companies. So they just literally took the top 13 maximum companies for median worker pay and went with that. It doesn't represent every company in America, for example, unless they had specifically a random sample. So since the 13 companies is not a random sample, these data are not representative of the population of all companies. Of all companies in United States of America, USA. So I would say this conclusion is not justified. It stands true for the 13 companies in the actual article. If the 13 companies is our population and that's all we care about, yeah, that's about right. The more they're getting paid, the more the stock price is going up. But when you read an article like this, you're thinking all companies, whether they be McDonald's, Starbucks, ISU, as for an example, things like that. And well, there were no companies like that in this data set whatsoever. So since the 13 companies is not representative of all companies in USA, the results do not apply. They could be true, but they do not apply to all companies. I'll just put an exclamation mark on that because to me, this is really subtle. The article states that companies that pay more are seeing a payoff in their stock performance. The article should never have said that. And this is not just a dig at USA Today. They don't have the best journalism, but this is just an easy mistake to make. This is implying that what you see in the scatter plot applies to every single company in America, but we don't actually know that unless we took a random sampling among all companies in America. So that's what part C is really about. It's a very open-ended question. It's meant to start helping us think about randomization as we're getting closer and closer to inferential statistics. Well, any last questions then, folks, with the conclusion to chapter 6? Okay, well, congratulations, folks. We did it. Let's save these notes up. Actually takes a minute for all this to save once the notes get kind of long. There we go. So finally, just a reminder, on our upcoming exam 2, it looks like it's going to start chapter 3, chapter 4, those are shorter chapters. Chapter 5, we broke up into sections, and it's going to end right on the things we were doing in chapter 6. So I'll have those right up soon. And if you want to get started studying soon on this exam, first, see to the quiz. That's going to be available Thursday morning, and that's pretty much you studying for the exam, working on that quiz. But we're now in chapter 7, so let's jump in and see what we're getting into next. Even though chapter 7 is not on exam 2, it'll be on the third exam, there's enough ideas that overlap in chapter 6 that we're still kind of studying chapter 6 concepts, so that's kind of helpful as well. Some books sometimes make chapter 7 a part of chapter 6 because it's just a direct continuation. But I kind of like when it's more granular, when they break things into different chapters like this. That way it's not too many topics all at once. Our example 1 is not something I'll ever ask you to do on a quiz, MyStats lab, or an exam. This is more of us just warming up to these notes, kind of like what we did in chapter 6. So let's start off. It says here, the equation of a line is that. That's weird, right? In the math class, you'd never really write your equations of lines this way. So let's try to connect back to what you might have recalled. In a math class, you usually write y equals m x plus b. So that's what we were doing in prior math classes. M would be the slope of the line. B would be the y-intercept, where the line crosses the y-axis. And that's all really wonderful, except in statistics, they have good reasons for this, but in statistics, they don't write their equations like this. Let's take another quick look in the calculator. In the calculator, when we went to go calculate the correlation coefficient, we went to the stat button, calculate. And on this menu, we didn't use ax plus b because our line is not going to be written this way. We're using option 8, a plus bx, because our equation is written this way. Except our book likes to get even more special. Other books that we used in the past did actually use a plus bx. That was kind of nice. Our book uses b naught for their a value, so there's a little bit of a translation layer there already. B naught is the y-intercept. Much like this b was in an ordinary math class. All we've done is we changed the order of the terms. The intercept comes first in statistics. I don't know why they decided to do that exactly, but it's a very well-established pattern. And the slope is the value that's the coefficient to x, the number that's multiplying x, in other words. So again, that's the reason why we're using option 8 over here in the calculator, just so that we're always using the same kind of thoughts and we're not having to change too many things over. Well, B1 is the slope. It's going to tell us how much the line rises or falls when x is increased by 1 unit. B0 is going to be the intercept, and that's just the height of the line when x equals 0. I think this is highlight worthy because we'll have to look and calculate intercepts. And this is a good thought right here for what its interpretation would be. Well, any questions, folks, with the write-up here? Okay, and just for the sake of practicing a little bit more, we're going to plot one line. Again, this is not something that we're going to do all the time in this class. This is just a way to get a feel for that brand new equation and how to work with it. So we started with the line down below by writing it in the way a statistics class would. So -5 comes first. I'll try to keep this color coding consistent on these notes. That's now the intercept. That means the slope is 7/3. And if we were to go to graph this by hand, it would look about like this. First point you want to put down is the one on the intercept. It's always the number that doesn't have x multiplying, and it just tells us where on the y-axis you have to go for the curve to cross, the line to cross. It says you go down 5 units. So 1, 2, 3, 4, 5. And that puts us right here. I'll use blue here to convey it came from the intercept. Any questions about that step so far? Okay, then this is the slightly more mathy part of all this. We use the slope to get to the second point, but it's really just a set of instructions to go from that point to your next one. Because there's a positive sign, we will go up 7, and for the denominator, I always move to the right. In fact, if there's a negative sign, I think of the negative as multiplying into the numerator to say down 7 if there was a negative, but we would still go right through. So back to here, this was down 5, so up 1, 2, 3, 4, 5, 6, 7, right 3, 1, 2, 3, takes us to that point. Green tick marks are just to convey we got to that second point from the slope. And here's the whole line. You go from here through here. If it bends a little, that's okay. Now this is y equals -5 plus 7/3 x. So our calculator is going to be doing a lot of this for us, but it's good to just see how does it come together at least one time, since we're going to be working with that equation on these notes. Well, any questions, folks, for the warm-up phase of getting through these problems? Okay, so we're dealing with equations of lines only because we want to put a line down to these kinds of things. So for putting a line down to it, we should know how to build it and how to work with it. So coming down below, here's where the notes gets a little bit dicey in a certain sense. Here we're trying to explain how the line actually gets built in the first place. So think of this part of the notes as being similar to when we were here on the chapter 6 notes, and we did weird stuff on this display to just try to convey how the formula is working. So these are never things that I'm going to quiz you on again or do an exam question on again. It's more just trying to piece together what in the world is the calculator going to do when we actually make it produce a line. So here's how it goes. It says here, a widely used measure of a bit of a line, we call this y hat equals a plus bx, to bivariate data. That's just saying two quantitative variables. The bivariate means the two variables part. That means we have a set of coordinates, x1, y1, just like these points we see out here. So what we'll do is calculate this. Y hat minus a plus bx. Y hat is the predicted value. And we get all these values coming up in this way. The least squares regression line is a line that's going to minimize every single one of those values so that the sum is as small as possible. That's kind of weird, but that's what the line is supposed to do, minimize all of this stuff. Any questions about that so far? Okay, so algebraically writing it down with math symbols, this is what it all looks like. I think it's easier to visualize this by just simply putting down an actual line to the data. So let's say we did find that line and the technology plotted it. It might look something like this. So this is the equation. Y hat, the hat is this up arrow we're putting on the y variable. So that's read as y hat equals a plus bx. Y hat is also referred to as the predicted value. And what we mean by that is the purpose of this line is to model data. So for example, if we, just for a really quick illustration, put in a value of say 100 on this line, we would take 100, go up to this point, and that value would be y hat, the predicted value when x was 100. So we can make some predictions. Although this one's dangerous, it's far out of where the cloud of data points is. That would be considered extrapolation. We're not getting into too much of the vernacular, but just in case you've heard that word before, that's the kind of stuff that comes up in regression. So we've got an equation of a line. Like before, we want to calculate the slope of this thing. That's going to be the b coefficient. And sorry, I already made a mistake. We typically write this as, in our book, b1, rather b0 plus b1x. Sorry, that was my mistake there. I already forgot that we're not using a plus b. So we go and take b1. b1 is the slope. And if we ever had to calculate it by hand, this is how you would do it. It's kind of amazing. It uses the correlation coefficient r itself. Then you just take the fraction, standard deviation of the y data, divide by standard deviation of the x data, and it calculates b1. But what's more amazing about that is somehow, some way, the correlation and the standard deviations are giving you the right slope so that this sum of deviations is minimized. There's no other way to do this. Then you just calculate the y-intercept in this way. You take the mean of the y data, subtract the b1 value, slope from earlier, times the mean of the x data, and you get the y-intercept. So that's how that all comes together. But there's another thing you can do to visualize this. When you go to write out y hat is b0 plus b1x, so that equation up here, y hat, like we mentioned before, is the predicted value. But another thing comes into the picture, something called the residual. So let's be really careful with this plot to get a good understanding of what a residual is. Let's use the color purple to make it pop out. So when we look at any data value, say this one right here. Let's decide on a color. Let's go with orange. This would be a y value because this is an actual observed value from the data. So when the residual says it's E for the residual observed value minus predicted value, they're talking about Y for the observed value, something that's actually in your data set. But it's an observed value minus a predicted value. What's the predicted value? That's the thing that we write as Y hat, the predicted value of Y. Here's the new thing. The moment we find this line, the one drawn up here, well, we have a conflict. There's the actual value that you see in the data, and there's the value that would be predicted. It lies directly perpendicularly above. that causes this distance. This is thought of as a bit of an error, or you could call it just residual. It's visualized this way. So that's the error between what you actually got in your data versus what the regression line, the one trying to get the closest to all the points, actually would produce. So this is a residual. It's equal to y minus y hat, but it looks like this on the graph, that distance there. Any questions, folks, about visualizing that residual? Okay, I think residuals are kind of tough, but this is my personal opinion. I think what's not tough is the equation. It's just always y minus y hat. What's tough about it is the interpretation of what you're really looking at when you're finding a residual. So let's write this down just to get a little bit more of an understanding. Let's come up here and just focus on that graph. The residual y minus y hat is the difference between the real data value, y, and the value that is predicted by the regression line y hat. So it's measuring a distance. And well, when we say we're minimizing the sum of the square deviations, what we mean is we're taking that y minus y hat, raising into a power 2, and it goes into these equations. It's minimizing the square distance of the residual is what's really happening, in other words. Let me take those things off so that doesn't get too crazy in the notes. But that's what the residual is. We square those distances, we only have positive measures now, and this won't sum up to 0. If we didn't square those distances, the distance between the residual, all those values here, the residual values, they would all actually add up to 0, giving us nothing meaningful to work with. That's the same conflict we had with standard deviation. That's why we square things, so we get an actual positive measure. So we're squaring all these lengths, adding them all up, and that's what that looks like. And this line is the one and only line that makes all of those distances, when you square them, as small as possible. Kind of crazy. There's a huge, huge amount of mathematics that goes into this. But the cool thing about statistics class is we take all the mathematics. Technology is going to do the calculations for us. We're more interested in the interpretations. Nonetheless, it's good to know how does this all come together once, at least once, before we just start throwing things into a calculator and have it spit out results. This is the picture in your mind's eye of what's going on in the background. Well, any questions at all, folks, with that discussion here about the regression line? Okay, this is a really tough thing to talk about, to be totally honest. Author does a pretty good job, so seeing it in the reading is helpful. Seeing it kind of drawn out this way is helpful too, but really it comes together more and more once you've just done regression a lot. By the time you've studied for the final exam and you're doing this problem again on a real final exam, that's when it starts to make more sense. So I'd say don't worry too much if this just seems completely crazy what we described here. It's more about getting the correlation value out. We don't have it on that notes. And this is more just helping us out seeing what's going on in the calculator. I'll never ask direct questions about this kind of material here, nor anything on this plot here. However, questions can come up from the residual, so this is still a useful equation down below. Let's say that's right here. This is an important equation. So that's our bigger takeaway. We'll come back to that equation in the notes as we need it. And now, for example 2, let's model some data. We're going back to the problem with the algal blooms or algae blooms, because we've seen the scatter plot before. We produced it on our calculator. Here's it produced again. And by the way, if I'm producing a scatter plot for you on a quiz or exam, it's going to be graphics about like that. Let's make it a little bit bigger. Let's remind ourselves of the context as well. So we have algal blooms or algae blooms. They have negative effects by dominating the phytoplankton communities. And this is one algae we're interested in. This must be a particularly bad one. So just a quick look up. This is what the algae looks like. Just a bunch of stuff like that clump together, I suppose. I'm not really a marine biologist, but that's what we're looking at and what we're trying to control. And what we're doing next is we're trying to see how well they're being controlled by putting these algae in a test tube and introducing something inside that test tube. These little critters. So this is what munches on the algae. I don't remember this being a pretty picture, but let's look at it again. So that thing there, some weird little creature, is what's chewing on the actual algae that's controlling its growth. So they place them in a test tube. When it says number of grazers, they're referring to that thing there. So let's start color coding this up. First row is going to be the explanatory variable, which is the grazers. Second row is the response variable, and this is referring to the growth rate of that algae. So it's not that algae specifically, but how its rate of growth is being affected. It's all negative to indicate it's being slowed down. So we've got the findings, and it says right here, for part A, calculate the least squares regression line. Then plot this line on the scatter plot above. So I won't ask you to produce a scatter plot, but you might have to put a line to it. That's something we can do right away. And the only way you would lose points is if you did something, say, like this. There's no way that's the best fitting line, right? It's got to try to get as close to those points, minimizing the residuals. So I'm expecting usually something about like this. And it doesn't have to be perfect. If it's in the ballpark of something like that, a line approaching points, then I'd say that's terrific. You're not required to plot this perfectly. But we can get the actual data on the equation, so that's what we'll do next. Any questions about the data so far before we go get that regression line?
The reason that the number of grazers is the independent value is because you control how many you input, right?
Exactly, yeah. That's a great way to think about it. We're controlling how does the net growth change as we're putting more and more grazers inside the tube. So it's the thing where, I like how you said that, directly controlling or influencing. That's a great way to think of the explanatory variable. Other questions so far? Okay, well, let's go back to the calculator. This one is a little bit easier to import. So first thing to do is hit stat key, hit enter right away. Standard trick, so you don't have to hit the delete key like 30 times, is just a clear in that way. You have to make sure the very top is highlighted when you go to click the clear button. And one thing you definitely don't want to do is when the top is highlighted, definitely don't hit delete. It will go away. You could end up deleting all your variables, but let's just say that's happened. Suppose everything's gone and we don't know what to do. All you want to do is hit the stat key, go to the very bottom option, setup editor, hit enter. Something happened. I like how the calculator just says done. You wonder what in the world really happened. But hit the stat key again, hit enter again, and all your stuff will be back. So nothing's really gone. So for the L1, that's explanatory. So go 1, 2, 3, 4. L2 is the response. So net growth rate, negative 1.9, negative 2.2, negative 4.1, negative 4.3. So we've got our data. Next thing we hit is stat key again. Go over to calc for calculate. We don't want one variable or two variable statistics. We want the equation of the regression line. So we'll go down, definitely skip past 4, unless you're not opposed to just changing the order of stuff, and you'll be all right. Go all the way down to option 8. This is the one that gives us the regression line. It's also how we got correlation. So it's kind of nice that there's overlap there. Hit enter a bunch of times. And this is what you should see. So when we go to write our regression line, it goes in like this. I often write y hat to remind ourselves that these are going to be predicted values every time we use a line. If you wrote just y, there's no harm done. It's more of a stylistic choice, in all honesty. It's going to be equal to intercept first. In this calculator, that's indicated as the number that's right in front, the A value. So it's negative 0.85. Then it's going to go minus, because the B value is a negative 0.91. So minus 0.91 multiplying X. So this is what I would put down on paper after getting this result right here. But let's actually do a screenshot. I want a screenshot of just this much, because that's what's pertinent to this problem. When you go to do this in your calculator, it's essentially doing this. For those who are a fan of arrows, first number is your intercept. Second number is always your slope. So that's how we put the line together based on what we see in the calculator. Any questions, folks, with producing that equation?
That's the line with A minus BX. Right.
Yeah, it's a plus a bx, but our b is a negative. So yeah, it turns into a minus. Other questions so far? Okay, well, congratulations, folks. That was an extreme amount of computation. And again, it's always cool to see this was something that could take hours this time to really calculate from scratch, doing every single part of this computation. But the calculator did it in just a matter of, I'm not too sure, proportions of a second. Now what we want to do is start working with this model. And again, a lot of what we're doing is just interpreting what we see using the context of the problem. So these are pretty required statements that go along with each one of these problems. First thing we want to do is give a practical interpretation of the y-intercept. So when it says the y-intercept, it's always referring to the very first number. So follow the color coding. That's always going to be your guide on these notes. I'll be very careful with blue for intercept, green for slope. Other thing that you might want to say, though, when you're thinking about y-intercept, is that the y-intercept occurs at x equals 0. So that's an important thing that happens for every single y-intercept. The reason that's important for us is the moment you set x is 0, you're talking about the explanatory variable x up here. It's this axis we're working on then, x-axis going that way. So we're saying at x equals 0. Well, that would mean no grazers in the test tube, right? That's going to be our hint on what's going on just by thinking of the context. At x equals 0, there are no grazers. So now we're ready to give an interpretation. And pretty much, this is how I would think about it on every one of these problems that goes along these lines. Sometimes the intercept makes no sense at all, and we just have to say that. That's going to be on the next problem we see on our Thursday's class. But here we can now say the y-intercept of negative 0.85 is the, well, if it's a y-intercept, it's on the y-axis, right? That means it's referring to the y variable, which is net growth rate in this problem. So we'll say at the y-intercept of negative 0.85 is the net growth rate of the algae when there is no grazers in the test tube. Forgot how to spell test. Let me try again. So that's what's happening with the y-intercept. It's not even on this graph because we didn't even have 0 on the data. But if we move backwards and went higher on the line, it'd be some value up here. It'd be growing even faster because there's nothing munching on it. The rate it'd be growing, well, recall, at a y-intercept, you throw x equals 0, so that's just gone. That's the net growth rate. It's growing at negative 0.85 for their growth rate. So we said here, the y-intercept of negative 0.85 is the net growth rate when there are no grazers. So that's how we interpret an intercept. Does that make sense to folks on thinking in those terms? Okay, let's try this out again. Notice this is a tough problem because when you go to use the context, there are two variables this time, and each one of them has different roles and they're related. So there's a lot of things going on. So each time I do this kind of problem, I'd really want to be looking at this. Not a bad idea to add extra graphics to your own scatter plot just to organize what's X, what's Y. And let's just take a huge screenshot right here, like this, so we can think about the next problem. Let's dump it down here. And the next thing we're going to try to interpret is the slope of the least squares regression line. Well, dang it, I need one more thing. Let me pull down the actual least squares regression line. Just trying to carry everything down so we're not scrolling up and down a whole bunch. I would imagine that gives people motion sickness after a while. Okay, we're ready for the next part. It says, interpret the slope of the least squares regression line. Slope is always the thing that's multiplying X, but slope is a tricky object. Let's put it in carefully and write out negative 0.91. Next thing we want to do with this, again, there's always a little bit of preliminary work before we even get to the interpretation. We want to convert this into a fraction. Good idea to keep the negative sign in the numerator, negative 0.91. Put in an extra long fraction bar, and it becomes a fraction by putting 1 down below. So you can always field promote any number whatsoever into a fraction like that. Next thing we do is, well, a slope is a rate of change. When we say rate, we're thinking of things like miles per hour or dollars per week, anything like that. There's always two kinds of units. Here, there'll be a unit for the numerator, a unit for the denominator. Anyone happen to know by chance what the unit should be for the numerator? I think it's kind of a tough question. Yeah. Good call, it is. It's always whatever the unit was for the y-axis. So that was number of grazers, and that's the unit that goes here. So let's put here number of grazers, or excuse me. Oh, I said that wrong. Going this way, it's the y-axis. It was net growth rate. Sorry, I got that one backwards. So the y-axis had a unit of net growth rate. That mistake is on me. Sorry about that. So we take the unit that goes with the vertical axis, divide by the unit that goes with the horizontal axis. Horizontal axis was grazers, or number of grazers. I'll just abbreviate it to grazers. But let's put a little bit of notes on this because this is tricky. This is the response variable unit, and that one is always the explanatory. Variable unit. So let's think about this a little bit more. The slope is negative 0.91. We divide it by 1. Here's another way to visualize it. If you take any point on this graph, here's my point right here, then recall how we found a second point on the graph. We just used the slope. In the slope that we indicated, we'll be going right by 1. So down here, right by 1, that's a pretty far distance. It'd be about something like that. So that's right 1. Then we have to go down by negative 0.91. So we're going down here. And that's what the slope does. It is the rise or fall. We usually just say rise over run, knowing that rise can be an actual fall if it's negative over the run. But rise, that's just the unit going this way. Again, that's the net growth rate. Run is just a unit going this way horizontally, and that's the unit for the number of grazers. So some people visualize it this way better. Other people just like the quick mnemonic here of The numerator is always the response variable unit. So that'd be the very first thing I'd want to do for a problem like this. To give a good practical interpretation of the slope, it's not easy. This is a trickier one. It's trickier than the intercept. But with all this preparation, here's what it would look like. I'm writing this here, practical interpretation, just to convey this is where the answer is. When it asks for a practical interpretation, I want to leave the graphics down below just to show how we got there. But my answer is going to be right here. So finally, when we go to interpret the slope, the value negative 0.91, we turn it into a fraction and we just say this. Focus on the denominator first and say, for every additional razor put in the test tube. So we're referring to the denominator. We put an additional grazer in the test tube. So that means on the graph, we moved to the right by 1. But to get back to the prediction line, we had to go down by a certain amount. And that's what we say over here. By looking at that numerator unit, we'll say the net growth rate goes down by 0.91. So that's our interpretation. To make it a practical interpretation where we use the context, we had to say for the additional grazers here, and we had to mention the net growth rate here, just using the explanatory variable and the response variable. Kind of the way we gave an interpretation for a correlation. We're just saying the value, saying how they're related, mention the variables, and then you're all set. Well, any questions at all, folks, with the written statement here? Okay, I think it's really tough because, again, in a math class, people are just happy with that value, the value of the slope. People are happy just to show what it looks like graphically, but now we have it 3 different ways. You look at the slope, visualize it by thinking in your mind. For each additional grazer, the net growth rate goes down by 0.91, and you've got that interpretation. This is essentially what the MyStats lab is going for their interpretation. So when you see the multiple choice for a question like this one, just make sure that nothing looks a little bit weird. They'll try to say it goes up instead of going down. It should say going down if there's negative. So look for just the anomalies like that, and you'll be all set. But let me box this one out because there's a lot of work on this problem. I just want to convey that's all you have to say, but this is a good setup to get to that part. Any questions at all, folks, thinking about the slope on the model? Okay, definitely a little bit tricky on these kinds of things. And this is where it all gets a little bit easier. Part D says, calculate the predicted net growth rate for 2 grazers. Now, that's a weird problem because you already know at 2 grazers, the experiment gave us a net growth rate, negative 2.2. But what we're asking is, what if we put 2 into the model? We would get a value that's right around here. And we're wondering, what is the predicted value? So let's give this a try. When it says 2 grazers, let me use just yellow highlighting for that. This means X equals 2. So that's not too bad. We go right up here where we had the model. This is from part A, and write Y equals negative 0.85 minus 0.91 multiplied by 2. All we're doing is putting in an X value and seeing what we get. Does that make sense to folks on that step? Okay, so this is kind of the funner part of the computation. I'd say anything with slope, anything with y-intercept, be really careful with those. Those are tough interpretations. We'll do another problem on these notes, potentially a 3rd problem if we feel like we need more practice. But these are the funner questions, I think. So in the calculator, just go negative with the negative sign, 0.85, minus, but this time with the minus sign, that's a little tricky, 0.91, parenthesis 2 for times 2, or you can just use the multiplication symbol. And we get this. Predicted net growth rate is negative 2.67. And one thing I didn't do is I didn't put my y hat on there. Again, that's not required, but it's good to put on there just to emphasize that's the predicted value. Let's take a look. The actual value is negative 2.2. So at a 2 value here, 2 grazers, we got negative 2.2. It's this number up here. But the model gave us that number over here. And so now there's a distance, E, which is the residual. So now we get to calculate that residual. That's just an equation that was from up above. It goes like this. Calculate the residual in part D. We take E equals Y. That's the observed value in the data, minus Y hat. That's been the way that it is a good idea to put a Y hat right here because it's going to organize your results when you go to use that equation. Where we get Y from is right here. Reason being is we're looking at 2 grazers and we're calculating the residual relative to 2 grazers. So this is our Y value, negative 2.2. Let's just say here, part T, negative 2.2, once I get the actual pen to work for us. Then we go minus Y hat. Y hat is what we just calculated, the negative 2.67. I think the tricky thing about this is there's extra negative sign in the middle, so that's going to really convert to plus. But if you just input this in really carefully, you'll be all set. Calculator can do the order of operations for us. So it'll be negative 2.2, they go minus for this, a parenthesis, a negative sign for this one, or you could just type a plus right here in the middle if you want to save some steps, 2.67. And that's our residual, 0.47. It came out positive, and what that tells us is the actual real value is 0.47 higher than the predicted value. So the residual turns out positive. Well, that's a pretty tricky set of problems there. I think this is really hard to absorb the first time, so we'll be practicing this additional times. Again, we'll do another problem on Thursday, and I might think about bringing in a third problem as well, since I think 3 problems is good for this kind of information. But any last questions, folks, on how to put all that together? Okay, well, give this a try in the homework when you get a chance. And it's pretty much going to be problems just like this one. If you're a person who likes to work ahead, you could probably get pretty far in the homework at this stage. But no harm in waiting until we finish off this section officially next week before you dive in. In fact, with the upcoming exam 2 coming up, you might decide to focus on the chapters 4 through 6 homework, and that would be a pretty good strategy, I'd say. 3 through 6, thanks for correcting the record on that. I need to put in that information soon, I'm sensing. Well, that's all I have for folks today. Thanks for your hard work, and I'll see you all on Monday's class.
Thank you.
I'll see you on Thursday's class. Yeah, sorry about that. I have a Monday, Wednesday only class, and I told them good, a happy weekend, but forget, we got one more day. Thanks for reminding me. No, we do officially have one. And I hate to cancel it because we do have a Halloween class that I am thinking about canceling, so.
I have kids, that would be phenomenal.
Yeah, a lot of people have kids, so we're probably gonna cancel that one. That's why we haven't canceled anything so far. I think it's just rude to run a night class on Halloween. There's almost no one on this campus anyways.
Restaurants, that's great.
Yeah.
That's gonna be